Welcome. In this video, we're going to review solving matrix equations, specifically for the cases of 2x2 and 3x3 matrices, and we're going to solve them using inverse matrices. Right, to begin, it all starts with systems of equations. For example, consider the system of equations, say 3x plus 2y equals 5, and perhaps x plus 4y equals 6. In this format, we usually refer to it as a system of equations, two variables and two equations. We also might convert this to other forms. For example, gathering the coefficients of x, the coefficients of y, and the constants like so. The coefficients for x are 3 and 1. The coefficients of the y's are 2 and 4. And finally, it's equal to vector of constant numbers 5 and 6. In this format, we'd call it a vector equation. We can go even further in grouping our numbers. We can group together all of the coefficients, 3, 2, 1, 4, group all the variables into a vector, x, y, and the constants, 5, 6, and when we write the equation in this form, we would refer to it as a matrix equation. And finally, there's one other form which you might be familiar with. So if you gather just the values together, in this case 3, 2, 5, 1, 4, 6, and sometimes you'll see a dashed line to separate the constants from the coefficient constants from the constants at the end of the equation. We'd refer to this as an augmented matrix. It's not really a matrix equation because there's no equality sign in there, but often we'll take an augmented matrix and we'll do row operations to bring it into a simplified form where we can read off the answers more simply. But today we're going to focus on solving matrix equations, specifically for the 2x2 and 3x3 cases. All right, so again, I'm going to write down that example of a matrix equation of 3, 2, 1, 4 times the variable vector x, y equals 5, 6. Now this has the general form of a matrix A times a vector V is equal to another vector W. Now, if we're able to calculate the inverse of a matrix A, we could multiply both sides of the equation by the inverse matrix. And the defining characteristic of an inverse matrix is when you multiply these two together, you're left with the identity matrix, which you might recall is a certain patterns of zeros and ones. And when you multiply anything times an identity matrix, you're left with the original value. So if we're able to calculate the inverse of a 2x2 matrix, that provides a way to simplify these equations. For a 2x2 matrix, there's a pretty nice formula for that. If your matrix has the general form A, B, C, D, then a formula for the inverse is 1 over the quantity AD minus BC times, basically rearrange the values in the matrix, the numbers in the DNA positions swap, main diagonal, and the other entries are negated. And this, in fact, gives you the inverse matrix. When you multiply A times A inverse, you'll notice you get the matrix I, which has 1, 0, 0, 1 in it. The identity matrix for 2x2 matrices. So we'd like to use this approach in order to solve this equation. So we've got our matrix right here. We can calculate, we can find A inverse using that formula. First, we have 1 over A times D minus B times C. See, 3 times 4 minus 1 times 2. So that's 12 minus 2. That's going to be 10. Times, let's rearrange those numbers, stated by the formula. If we want to, we can carry this scalar multiplication through and simplify it a little bit more. Right, so the top row will become 4/10, also known as 2/5. Then we'll have -2/10, or -1/5. We'll have 1/10 times -1, and 1/10 times 3. And that's the inverse matrix. If we want, we can check that that's the inverse matrix. It's always good to check. When you have time, you can be extra confident of your answer. So let's actually multiply together these matrices. So I have -2/5, -1/5, -1/10, and 3/10 times the original matrix, 3, 2, 1, and 4. You might recall, in order to multiply together two matrices, we actually do a series of dot products. Sometimes like to write in these dotted lines to remind us of how this multiplication works out. Right, so to figure out in the product matrix, the top left entry will take the left row, or sorry, the top row, the first matrix, times the left column of the second matrix. And we'll get, let's see, doing that dot product, 2/5 times 3 minus 1/5 times 1. It's at 6/5 minus 1/5, that's 5/5. Next, to find the top right entry, we'll take the top row, dot product with the right column. So we'll have 4/5 minus 4/5. That'll be 0/5. That works out well. On the bottom left of the product, we're going to multiply together, do the dot product of the bottom row, the left vector here. We'll have -3/10 plus 3/10 gives us 0/10. For the bottom right entry, bottom row, dot product with the right column, we'll have -2/10 plus 12/10. -12 plus 2. So we're going to get 10/10. And sure enough, that simplifies to the identity matrix. So that checks out. We can be pretty confident we've calculated it correctly. But next, we need to use it. Remember, the goal is to solve this equation over here. So we're going to end up multiplying both sides by this inverse matrix. All right, so remembering the goal here, we have 3, 2, 1, 4 times xy is equal to 5, 6. And we're going to multiply both sides by the inverse matrix. And when we multiply the left by the inverse matrix, we're just going to be left with xy. But maybe we'll put that in. We'll actually add the words multiply by A inverse on both sides. And then we're left with xy on the left. Then on the right, the inverse matrix. Let's check that again. It's positive 2/5, -1/5, -1/10, and 3/10. So 2/5, -1/5, and I've already forgotten it. 2, -1, -1/10, and 3/10. All right, we've got this, -1/10 and 3/10. Excellent. We're going to multiply that by 5, 6. Right. Again, I always like to, little visual cue there. When we multiply this out, let's see. Again, we're doing dot products to get the top entry, top row, dot that vector. So we'll get, let's see, we're going to get 10/5. That works out nice. Minus 6/5. Then on the bottom, we're going to do the dot product of the bottom row with that vector. We'll get -5/10 plus 18/10. And that simplifies to 4/5 and 13/10. In other words, we think the solution is x equals 4/5, y equals 13/10. So we should go ahead and check that. We're going to check the solution by plugging it into the system. Right, remember the original system of equations was 3x plus 2y equals 5, and x plus 4y equals 6. So let's go ahead and try that out. So we've got 3 times 4/5 plus 2 times 13/10. Let's see, this is going to be 12/5 plus, we can reduce this a little bit. The 2 and the 10 reduce to 1 and 5. So I'm left with 13/5. But 12 plus 13/5 is 25/5, which gives us 5. Right? That checks off with our first equation. With our second equation, see, we want to check that 4/5 plus 4 times 13/10. See, we have 4/5. Again, before we multiply this out, we can reduce the 4 and the 10 to a 2 and a 5. So we'll have 26/5, which gives us 30/5, which is equal to 6. Excellent, that checks out with our other equation. So we can be pretty confident we've correctly solved the system of equations. Now, I'm a big fan of the philosophy that you learn math by doing math, so I would highly recommend that you also work on a problem. So I'd recommend for those of you watching to try this problem. All right, I'm going to go ahead and give you a system of equations. Let's try 4x plus y is equal to 5. Let's also try 5x plus 3y equals, I don't know, 8. Let's not try 8. Let's try 6. All right, so for this, what I'd like you to do, go ahead, try to write it as a matrix equation. We can write this equation in many forms, but we're really interested in matrix equations today. And then go ahead and, before we solve, find A inverse, or by A inverse, I mean if you write this equation as A times vector V equals vector W, find A inverse, and also, because you can, should check that A inverse times A equals the identity. Once you've verified that that's true, go ahead and solve. And to solve, you calculate W. Actually, no, you calculate V, which is the vector of variables, as A inverse times W. And then, of course, again, we can check by plugging the solution into the original system. All right, so you should go ahead and give that problem a try, see how that works out. Now again, we said that we would be testing 2 different types of problems. We're going to use basically the same approach to solve a 3x3 matrix equation. And we're going to start with a system of 3 equations with 3 unknowns and try to apply the same techniques. So, onwards. All right, let's switch colors. Let's try maybe a red color. All right, so for this example, let's consider the following system of equations. Let's do 2x plus 4z is equal to 6. Maybe y plus 5z is equal to 4. And let's do one with all the terms. 4x plus y plus 10z is equal to 15. All right, and convert this to a matrix equation. And just like before, we'll gather all the coefficients into one matrix and be sure that your variables are lined up. Now, those variables which might be missing from an equation, they have a coefficient of 0, don't forget. So here I have coefficients 2, 0, 4, 0, 1, and 5, 4, 1, and 10, times my variable vector, x, y, z, is equal to 6, 4, 15. Again, this has the general form. Matrix A times a vector V is equal to another vector W. And as before, our goal will be to find A inverse, then to check that A inverse times A gives us the identity matrix, and then solve for the vector V, which we'll be able to write as A inverse times W. All right, so finding the inverse of a 3x3 matrix is a little bit more difficult. There's not a simple formula that we're going to write down, but instead we'll talk about a procedure which you can use to simplify it. In general, the idea is if you have some kind of a matrix A, right, you can do some elementary row operations on a matrix A to convert it to the identity matrix. Right, so maybe I'll write those row operations. You do a row operation and another row operation. Keep on going, do some number of row operations until you get the identity matrix. Right? So you get all these different row operations here. Let's go ahead and multiply both sides by A inverse. So on the one hand, I have A times A inverse. On the other hand, I have I times A inverse. And I'm going to simplify this in a very specific way. Right? On the one hand, I'm going to have Rn, R2, R1. I'm just going to write that as I. On the right-hand side, A inverse times the identity matrix is still A inverse. So this is a very interesting result. Again, these matrices, R1, R2 through Rn, they correspond to the row operations that transform A into the identity matrix. That same set of row operations that transform A into the identity matrix will at the same time transform the identity matrix into A inverse. So the procedure we're going to use to calculate A inverse, again, a procedure rather than a formula, we're going to perform row operations on the augmented matrix. It's kind of like an augmented matrix that consists of our original matrix A on one side and the identity matrix on the other. Our goal is going to be to turn the left-hand side into the identity matrix. And when that's done, as we've seen above, the right-hand side will become A inverse. Then we'll double check to make sure A times A inverse gives us the identity matrix, and then we'll use it to solve this matrix equation here. Again, there are potentially more efficient ways to solve this. In fact, you might notice that if I go through all the work of calculating row operations to find A inverse, I could have in fact did row operations on this augmented matrix from this matrix equation. But we're just exploring a different way to go about things today. So let's go ahead and give this a try. All right, so we're going to go ahead and start off the augmented matrix. Let's see, on the left, I'm going to have 2, 0, 4, 0, 1, and 5, 4, 1, and 10. Then on the right-hand side, I'm going to put an identity matrix with a 3 by 3 case. Right, I'm going to try to be efficient with my row operations here. My first goals, I'll kind of notate these in here. I'd like to make this first column, I'd like to turn that into 1, 0, 0. I'm going to try to turn that into a 1. I'm going to try to turn that into a 0. And that's going to motivate these particular row operations. So let's see, I'm going to take row 1 and I'm going to multiply that by 1/2. This is just some notation on the side to indicate what I'm going to do to each row. Row 2 I'll leave alone. From row 3, I'll subtract twice row 1. So row 3 minus 2 times row 1. Let's see what happens. See, the first row becomes 1, 0, 2. I have to perform these operations all the way across. 1/2, 0, 0. Second row, nothing changes. 0, 1, 5, 0, 1, 0. Last row, see, row 3. So this numbers, the set of numbers in the third row, from each of these, I'll subtract 2 times the number in the first row. So let's see. 4 minus 2 times 2 is 0. 1 minus 2 times 0 is 1. 10 minus 2 times 4 is 10 minus 8, which is 2. 0 minus 2 times 1 is negative 2. 0 minus anything times 0 is 0. 1 minus 2 times 0 is still 1. All right, good progress. Next, let's see. I'd like to go ahead and like to cancel out some numbers in the second column. I've got a 1 in this position, which is great, a 1 in the center. I've got a 0 above it. Now I want to turn this number into a 0. So I'm going to go ahead and subtract row 2 from row 3. Then we'll be done with the second column, making some good progress here. So row 1 stays the same, row 2 stays the same. I'm going to take row 3, and I'm going to subtract row 2 from it. Row 3 minus row 2. So first row stays the same. Second row stays the same. See, third row, 0. See, 1 minus 0 is 0. 2 minus 5 is negative 3. Negative 2 minus 0 is still negative 2. 0 minus 1 is negative 1. 1 minus 0 is 1. Fantastic. All right. Next, I'm going to probably take this in 2 steps. First, I want to turn this negative 3, like to turn that into a 1. And so I'm going to have to divide that row by negative 3. And then, in a future turn, I'll eliminate the 2 numbers above it on this side. All right, so the next step is going to be, let's see, I'll leave row 1, row 2 alone, and I'll do negative 1/3 times row 3. All right, so 1, 0, 2, and 1/2, 0, 0, 0, 1, 5, 0, 1, 0, 0, 0, 1. Let's see. Again, I'm multiplying everything by negative 1/3. So 2/3, 1/3, negative 1/3. All right, this last step, we're going to have to do a little bit of math with fractions, but they're not too bad. All right, to cancel out this 2, let's write down what it is I want to do. I'd like to get a 0 in this position and a 0 in that position. All right, so I need to subtract 2 times row 3 from row 1. I need to subtract 5 times row 3 from row 2. So let's take row 1, subtract 2 times row 3. For row 2, we'll subtract 5 times row 3. And row 3, I will leave that alone. All right, thanks to all these zeros, the first 2 numbers don't change. I know I'm going to get a 0 here. Let's see. So I'm going to have 1/2. I might just write down the numbers and then simplify them in the next step. I'm going to have 1/2 minus 2 times the number in row 3. So 1/2 minus 4/3. Next, I have 0 minus 2 times the number in row 3. So that's a negative 2/3. I'm spacing this out here. Then 0 minus 2 times the number in row 3 is positive 2/3. The next row is going to be 0, 1, 0. And here, I'm subtracting 5 times the number in row 3 from row 2. So 0 minus 5 times 2/3 is negative 10/3. So I've got 1 minus 5 times 1/3. For now, I'll just write that as 1 minus 5/3, simplify later. And 0 minus 5 times negative 1/3. That'll be 5/3. Last row, 0, 0, 1, 2/3, 1/3, negative 1/3. Okay. So, since the side on the left is the identity matrix, what remains on the right should be A inverse. Let's go ahead and write that down. Let's simplify that out. Let's see, I need common denominators for some of these. So let's see, this will be 3/6 minus 8/6. That's, see, 3 minus 8 is negative 5/6 minus 2/3, 2/3. See, minus 10/3. So I've got 3/3 minus 5/3. That's negative 2/3, 5/3. Everything else seems pretty straightforward. All right, very good. So now that I've got this, there's 2 things I want to do still. First, I'd like to check it. Right, there's a lot of row operations there, and I could have possibly made some kind of mistake in calculations along the way. So I'll go ahead and try multiplying this by the original matrix, make sure that works out, to the identity matrix. And then once I've got it, we're going to go ahead and use it to solve the original system of equations. All right, so let's go ahead and check. We're checking that A inverse times A is in fact the identity matrix, which in this case and is 1, 0, 0, 0, 1, 0, 0, 0, 1. Right, we've got some big multiplication going on. So let's go ahead and write these down. So I have negative 5/6, negative 2/3, 2/3, negative 10/3, negative 2/3, 5/3, 2/3, 1/3, negative 1/3. The original matrix A, that was 2, 0, 4, 0, 1, 5, and 4, 1, 10. Again, I'm a big fan of drawing these lines to partition the matrices into easily identifiable, words are hard, easily identifiable row vectors and column vectors. And to calculate the matrix product, we're doing dot products of row vectors with column vectors. All right, let's see. Top left, so I've got top row, dot with left column. I'm going to get negative 10 over 6 plus 0 plus 8/3. All right, and I'll simplify these in a later step. For the top center, I'm going to dot product top row, center column. Let's see, that'll be 0, then negative 2/3 and positive 2/3, so that's going to be 0. No, I said I'd simplify later. So, all right, negative 2/3 plus 2/3. Just very excited for this to work out. For the last one, well, this is going to be a big one. See, I'm going to get negative 20 over 6 minus 10 over 3 plus 20 over 3. All right. Next, let's see, now I'm on to the middle row here. So I need to go ahead and do a dot product of the middle row with each of these columns. So first I'll have negative 20/3 plus 0 plus 20/3. Well, that's nice, that's going to be 0. For the middle center, let's see, I'm going to have 0 plus negative 2/3 plus 5/3. Seems to be working out. For the middle right, let's see, middle row right column, I'm going to have negative 40/3. Let's see, minus 10/3 plus 50/3. Excellent. Let's see, bottom row, have 4/3 plus 0 minus 4/3. Excellent. Next, bottom times center column, that'll be 0 plus 1/3 minus 1/3. Then bottom times right, it's going to be 8/3 plus 5/3 minus 10/3. Now let's simplify this out. I have a good feeling about this. See this first fraction, negative 10/6. Do a common denominator, that's 16/6. That gives us 6 over 6, which is 1. Get a 0 here. Again, I need some common denominators. If I put these all over 6, I'm going to have negative 20, and positive 40. Also give me a 0. Second row, it's very much 0. The middle is 3/3, which is 1. Minus 40 minus 10 plus 50 is 0. Bottom row, so 0 is 0. Let's see, I've got 8 plus 5 is 13, minus 10 is 3 over 3, which is 1. Hey, that's excellent. So we're absolutely positive that this matrix is correct. Now we'd like to go ahead and use it to solve the original system of equations. Remember, that was the goal, is to solve the system, which was, let's see, it was 2x plus 4z equals 6. And we had a y plus 5z equals 4. And 4x plus y plus 10z equals 15. All right, so we can solve for the vector x, y, z by multiplying A inverse times 6, 4, 15. And A inverse, we recently calculated to be negative 5/6, negative 2/3, 2/3, negative 10/3, negative 2/3, 5/3, 2/3, 1/3, negative 1/3. Times 6, 4, 15. Go ahead and partition first matrix into rows if you like. All right, so let's see. I'm going to get some nice canceling here. Negative 5 6 times 6. It's negative 5 minus 8/3 plus, let's see, I've got 2/3 over 15. And so that's going to be 30/3, which is 10. Cool. Let's see, second entry. I'm going to have negative 10/3 times 6. It's negative 60/3. It's negative 20. I'm going to have, again, minus 8/3. Then I'll have, let's see, 5/3 times 15. Let's see, the 15 and the 3, that simplifies a little bit to 5, so that'll be plus a 25. For the last entry, I have 2/3 times 6. That's 12/3, which is 4, plus 4/3. See, minus, simplifies to 5. See what we can do here. So we got 5 minus 8/3. See, 5 is the same as 15/3. So that's going to be 7/3 when all is said and done. So I have a minus 20 plus 25. That's going to give me 5 minus 8/3. Well, that seems familiar. Same thing as 15/3 minus 8/3. Once again, 7/3. See, here we have 4 minus 5. That's negative 1. 4/3 minus 1. That's 1/3. All right, so we claim that the solution is x equals 7/3, y equals 7/3, and z equals 1/3. To check that, we can go ahead and plug those numbers in, see if everything works out. So we're going to go ahead and plug into the system. Let's see. We've got 2 times 7/3 plus 4 times 1/3. So it's going to be 14/3 plus 4/3. That's 18/3, which is 6. Hey, that checks out. Next, I'll have the y, which is 7/3, plus 5 times 1/3. It gives me 12/3, which is 4. Well, that also checks out. Finally, I'll have 4 times 7/3 plus another 7/3 plus 10 times 1/3. How many thirds do I have? I've got 28. 28 plus 7 is, let's try that again. 28 plus 7 is 35. Plus another 10 is 45. So we've got 45/3, which is 15. Excellent. The answer checks out, so you can be very confident of our answer.